Okay, today I decided to do an air friction simulation. So, in most cases, people are told disregard air friction, um, which is probably fair for most cases, but I decided to do it today. And I have all the equations here and some code, and I'll walk you through it. So here, this is the formula for air friction right here. And the air drag on any object is given by v prime, or acceleration, equals alpha times v squared plus beta. And in this case, beta contains gravity and alpha contains drag. And to calculate alpha, since b is just 9.817 on Earth, it's pretty simple. But to calculate alpha, we're going to use this formula right here. 1 over 2 times the mass of the object times the drag coefficient of the object times rho, which in most cases is just air density, times the cross-sectional area that's exposed to your air or your fluid. So in this case, I'm going to do it with a 10 kilogram sphere with a radius of 1 meter. I know that's a pretty pretty large sphere, but just for this purpose, it's fine. So the drag coefficient for a sphere is roughly 0.47. For the atmospheric pressure, it's 1.2250. So you can see there, and area is pi r squared for a circle. So I did the calculation while I wasn't recording, and and alpha for a sphere of 10 kilograms and a radius of 1 meter is roughly 0.0904. And beta, like I said, is just 9.817. Now in the code, you'll see it's negative 9.817. That's because I'm adding it and not subtracting it. So in this part here, it's pretty self-explanatory. We'll just define the variables, right? Mass, radius, drag coefficient, air pressure, area, and alpha. So now we get to the libraries and the actual code. So what I've been using here, I don't think I need PyLab, but anyway, what I've been using here is SciPy, NumPy, Matplotlib, and I don't think I'm using PyLab. I just imported it because I was using it for something else. But from SciPy, I'm going to use this differential equation solver called ODEINT, Odient, I think it's pronounced. Not very sure. I'm not very comfortable with differential equations yet, but part of the reason for this channel was to try and teach myself as well as other people, but mostly myself, so I'm learning it. NumPy, just most Python things need NumPy just for basic functions. Like here I use it to get pi, and there's just other random things. And then Matplotlib to plot the data. There. So here, just define all the variables, same as up here, same variables, and if you try and recreate this simulation, it's very important that this line is the same, 1 divided by 2 times m in parentheses, because I was running into a problem where it was 1 divided by 2 times m, so it was half m times coefficient times pressure times area. So it's very important that you use parentheses. And I will run all of these. I forgot to do that. And here I'm defining the equation. And this is just dv dt, which is acceleration, same as up here, same thing as v prime. And this is just the equation that gives it. So same as up here, alpha times velocity squared plus beta. And just the way that this one works, this ODEINT, the way that it solves equation is it has to take a v at position 0 argument, and it has to take a range of times you want to solve it from. In this case, t is going to be our times. And here's another instance of NumPy. I'm using linspace. So it's taking 1,000 points from 0 to 5. And that's our time. And it's a unitless number. We could say 5 seconds or whatever. But anyway, so that's our function, and here I just called it solution, and it's going to output a list of all the solutions to this differential equation using ODINT. So I'll just run that, and this will just plots everything. So I'll run it now. So this is the velocity of our 10 kilogram 1 meter sphere. As you can see, starts at 0 because we decided to say v at 0 equals 0. So it starts at 0 velocity and just kind of falls down, right? And it gets to a little below 10, negative 10 meters per second, which is just, well, it might not be meters per second. It might be, though. It's probably meters per second. But it gets a little bit below minus 10, and then it reaches its terminal velocity, which is where it stops accelerating. And if you can see that you can see that if you plot the derivative of it. If you plot the derivative, you see where where the change starts to go just to 0. And that's when you've reached terminal velocity. So now let's take another example, and I haven't done this simulation before. I'm doing it on video for the first time. So I'm gonna take, this time we're gonna use a streamlined body. I don't really know how to calculate drag coefficients that well, so I just looked up on Wikipedia some drag coefficients, and a streamlined body is optimized to have the lowest drag coefficient, so I think that'll be interesting to see. So for area and everything, it's the same formula because it kind of looks like a water droplet, but the cross-sectional area is still pi r squared. So let's call it radius 1, so 1 meter radius, a mass of 5 kilograms, and the drag coefficient is 0.04. And then the air pressure is 1.225. And then that's our area. So now we have alpha. Alright. Run that, and now we have alpha. And since we've already defined beta and dv dt, we can just call solution again on the same function, just with a new alpha. And it should adjust. I'm just going to call the function again, and ODINT, it takes your function, your initial velocity, or your initial position, I guess, and your time. We'll use that same thing, dv dt, dv dt, and v0, and time. So that we should now have solution, and it should give us the stuff for streamlined body. So plot, and I'm going to say so my spelling's pretty bad, so if I spelled solution wrong, just ignore that. But we should, it should be plotted here, and this should head to S again. So yeah, that looks about right. So that's our solution for a streamlined body. So you can see it goes much lower than the other one did. It goes to close to negative 25 meters per second. I didn't add the time axis. Whoops. But anyway, there. So that's our, this is our just plotting the solution to the streamlined body. And here, now I'm going to show you the derivative. So this is just how fast the function's changing. That's essentially all it is. But it's very helpful for telling when you've reached terminal velocity in this case. I'm going to show you, and if I just type in the name of a variable, it will output the variable as long as you're using Jupyter Notebook. But see, when we use Odient, it will give us an array of our values of our solutions. That's true, right? But it gives it in a second array. It gives us an array of solutions, which makes more sense once you start doing multivariable things. But we're not going to get into that. So what I'm going to do is a dot p, which does a transpose. And as you can see, now it's in much nicer order. And it's also much nicer order for the computer to work with as well. So, but you can still see we've got the second array here. So we're going to take the 0th element, and there. That's our solution. So copy that, and I'm going to say diff equals p dot gradient of solution in relation to time, right? So I didn't plot it. Whoops. I have to plot it in respect to time, and there. The blue line is our derivative. So when the blue line reaches 0, or very, very close to it, like it's in other simulations I've done, it will get to like 1e minus 67. And at that point, for our purposes, we can call it 0. Once it gets to 0, then you've reached terminal velocity, and at the point where it's that value, that is your terminal velocity. And it shouldn't be changing much. So, that's how you do a derivative. Mr. P Solver has a video that is amazing on this very similar topic. So if you want to learn more about this, and not just the way that I'm doing it, definitely watch one of his videos. His air friction video, I think, is the very first one he ever posted. Excellent channel, highly recommend. That was my air friction simulation. And that kind of what it did for me was it taught me a little bit about the solver. But I hope you guys, whoever's watching this, enjoyed it, and I hope it's also educational, so you learn a little bit, or maybe not, but either way is fine. Well, thank you for watching. I hope you enjoyed the video. If you liked it, I would love to listen to any questions. I'll probably respond to them in another video. Just put them in the comment section. I'll probably read them. And thanks for watching. If you think I deserve it, a like would be great. Bye.